And some of you say, Eugene, why that's the case? Okay, so I'm going to sketch why. Okay. So now I'm going to sketch the flange section. So this is our flange, and these are our web. Okay, right. So what we want to do, let me get all this first. I need this figure quite a lot. Bear with me, okay? Okay. So where I stopped drawing, where I'm going to draw a line across. Right. So this is our centroid. Okay. So we know that this region is known as the flange. Yeah. So this region over here, or this part, is known as the flange. Okay. So we want to form the equation of the flange, right? Just a flange. Why we just choose the flange? Because it has a constant thickness. Right? We are aware that it has a constant thickness of 0.16 meter. When the thickness change, you have to form a separate equation. So that's where we call piecewise. So we divide them into pieces. Okay. So for this equation that we are going to form, we have a limit. Okay. So the limit is from 0.015 is the lower limit from the centroid, and the upper limit is equal to 0.035. Okay, that's why I say this equation that we are going to form has a limit of 0.015 to 0.03. Okay, so how does this work? So now we have a variable y. So I'm going to use a different color now. So this is our y distance. Okay, I put here. Okay, so this distance from here to here is our y. Okay, and the centroid of, so is this area that we're interested now. Now that y distance is your variable. You decide where you want to position y, but it cannot be smaller than 0.015. So it means it cannot go into the web section. It can only be in the flange section. Okay, so this is the area of interest. This is the area of interest now. And then we want to determine our y bar. Okay. So this distance is our y bar. Okay. So like anything else is the first moment of area, there is always complicating things now. Okay. So now we find our Q, Z, okay, and it's going to be as a function of y, right? And this is equal to width multiplied by depth multiplied by y bar. Okay. And we know that the width is a constant. Okay, so width over here is equal to 0.016. Okay. Now we have to find the depth. Okay, the depth will be equal to 0.035 minus y. Okay, that is your depth. And this is where we apply the rule where the analysis starts from y max, right? So the analysis starts from y max, right? So this is the analysis direction. That is y is equal to 0.035 minus y. Okay, so we apply the rules that we have developed. Then from here, the y bar is equal to 0.035 plus by y multiplied by half. Okay, so to quickly summarize, this is your width, this is your depth, this is your y bar. Okay, any question, anyone? Okay, right? So important that we apply the rules that I've written for you. Okay, the analysis starts from what? Y max. That is y 0.035 minus y. Okay, so the y bar, why is it 0.035 plus y multiplied by half? We have done this before. Okay, when I say we have done this before, probably we have done it in week 3, right? Where we want to find what? Where we want to find y bar, right? Where we want to find y bar, we have what? C plus y multiplied by half, where C is the maximum distance away from the centroid with the area of interest. Okay, so once you get that down, okay, it is so much easier. Okay, so this will be equal to 0.08. I think 0.008. Hold on, I think I got this wrong. This is 160. I do apologize. So this is 0.16. Okay. So this is also 0.16. So now this is 0.08. Then multiply by 0.035 squared, which is 1.225 times 10 to the power minus 3 plus by y squared. So this is over here is equal to 0.08 times 1.225 power minus 3 is equal to 98 times 10 to the power minus 6 minus, sorry, hey, wake up, Eugene, wake up. Minus by 0.08 y squared. Okay, so that is the expression for the distribution, for the function for the first moment of area as a function of y. Okay, so directly you can plug in your formula already. Okay, so shear xy as a function of y will be equal to the shear. So the formula is Vy over Izz Qz divided by T. Okay. So Vy we know is 90 times 10 to the power 3. Then we're going to divide by Izz 5 point, wait, I can't remember now. 5.813 times 10 to the power minus 6. And then multiply by 98 times 10 to the power minus 6 minus by 0.02 y squared. Right? And then we multiply by 2. No, 2. This is just 0.16. Okay. Now, question for you guys. How do we know that come on. Sorry. Computer decided to do something stupid. Yeah. How do we know that this is correct? Anyone? How do we know that this is correct before we go on? How do we know that equation that you form is correct? Anyone? Hello?
If you plugged in y equals 0, should it like return the value that you calculated at the centroid or something?
So the right thing to do, you're partly right, okay? Look. If you put y, substitute y is equal to 0.035, right? This equation should be equal to 0, right? So we plug in, so 98 times 10 to the power minus 6 minus by 0.08 multiplied by 0.035 squared. The whole thing has to be equal to 0. So I'm doing it now. So 0.08 times by 0.035 squared. Okay. Yeah. Then 98 power minus 6 minus by what I calculate, yeah, it's equal to 0. Okay. So because this value over here is equal to 98 times 10 to the power minus 6. Okay. That's the difference between A student and a B student. Okay. Nothing to do with how smart you are. Okay. God give us equal intelligence. I will tell you that. I'm not smarter than you. Okay. The only thing that's different is we know how to check our answer whether it's right or wrong. Does it make sense? Okay? That's what engineering is all about. Whatever you calculate, you have to sometimes sit down and look back. Does this make sense? Okay. And for example, if you have to calculate a stress that is 7 gigabyte, and then you sit down, you think about 3CO3. Eugene stresses that he calculated in the example usually is about 1 gigapascal. I'm getting 7 gigapascal. What does this mean? Something is wrong. Okay, so this is what an engineer should be doing. Okay, have a gut feel. I don't like to use the word, but I'll use it, a gut feel, to know whether your answer is right or wrong. Okay, right. So this will be equal to 90 power 90 power 90 power 3 divided by 5.813 power minus 6 divided by 0.16. That's by 98 power minus 6. So it will be equal to 9.483. Okay, 9.483 times 10 to the power 6 minus by divided by 98 power minus 6 times by 0.02. 1.9. I don't get it at all. 0.02. I think I make a mistake. Did I make it's not 0.02. 0.08. Okay. So 90 power 3 multiplied by 0.08 divided by 5.813 power minus 6 divided by 0.16 is equal to 7.741 times 10 to the power 9. Okay, y squared. So this is the equation of the distributed shear stress. Okay, I will do another one for the in the web section. Okay, in the web section, the first moment of area, there's a slight change. Okay, so the slight change, what do I mean by slight change? Okay, as I said, the problem with this topic is always the first moment of area. Right, so now what we're going to determine now is the shear stress equation. Oh, before I go on, sorry, I jumped so quickly without waiting for some of you to copy. Any questions from anyone, please? Okay. Yes. Luck. Oh, Lucas, sorry.
So would the shear stress equation for the whole thing be the equation for the flange plus the one for the web that we're going to find now?
It's not plus. This is just for the
flange. Yeah, it works in an interval. Okay.
Okay. And the important thing to take note is the limits. Okay. So this equation is only valid, okay, within that limits. Okay. Good question, Lucas. Okay. Anyone else? Any question? I see the attendance is dropping. Any idea why? Are you all busy? Go on. Isn't the width 0.16? It is 0.16, Devin. Okay. Okay. Right. Okay. Now then the next part is we are going to find the shear stress distribution in the web. Okay. And why we choose the web only? Because the thickness now is equal to 0.02 meters. Okay, that's the thickness. Okay, and then we have left and right. Okay, so where we are interested now is in the web section. Okay, let me draw our centroid first. So this is our centroid. Right. So now we are interested in the web section. And in the web section, we have a different limit, okay, of this equation. So the limit of